Okay, good afternoon, all of you. So, slight delay in the start of the session because there was some problem with the stream. Okay, it was buffering, so there was a problem, and so that is why a slight delay in the start of the session, right? So, so basically today we'll be doing hydrocarbons. Now, obviously, hydrocarbons is a very big chapter, so I don't think it will be possible to complete the whole of it in one session. So, what I was thinking is that maybe it will be a good idea if we can distribute hydrocarbons over two sessions. So, in today's session, we can do the mechanisms, and in the next session, we can do the rest of the chapter. So, okay, so actually, this is what I'm targeting to do today. So I don't know whether we'll be able to fully complete all of these, but this is what I'm targeting to do today. In this chapter, in this chapter, the four main mechanisms. In this chapter, the hydrocarbons, the four main mechanisms are free radical substitution, then electrophilic addition, then free radical addition, and electrophilic substitution. These are the four main mechanisms in this chapter. And in this chapter, there are two types of isomerism. One is conformation isomerism, and one is geometrical isomerism. So this chapter, these are the mechanisms, and these are the types of isomerisms that are there. Now, the thing is that electrophilic addition is also called so this electrophilic addition, it is also called Markovnikov rule. and free radical addition, it is also called Kharash effect. Okay, so these are the four types of mechanisms, and these are the two types of isomerism. One is conformation and one is geometrical isomerism. So I don't know whether it will be possible, but we'll try to complete all these things today. Okay, that is the target. If we complete all this today, then whatever is left in this chapter, we'll do it the next day. So, as per our discussion, we will begin with free radical substitution. Okay. Uh, these are some basic things we need to quickly look at before we discuss the formal mechanism. We just need to look at these basic things. Free radical substitution is the mechanism. Now CH4 plus Cl2 in presence of UV light, it is giving CH3Cl plus HCl. Okay. You know, these halogens have very high bond dissociation energy, and the halogen molecules, they have very high bond dissociation energy, and basically what happens is that the energy required to break these molecules, and also the energy required to trigger a reaction of alkanes. Alkanes are saturated, so they are not very reactive. So that energy has to come from a source like UV light, or it can come from lot of heating also, if not UV light. So in presence of UV light, CH4 plus Cl2 is CH3Cl plus HCl. We will discuss the mechanism, but before that, before we discuss the mechanism, one important thing is that you need to remember the order of reactivity is F2 greater than Cl2 greater than Br2 greater than I2. This is the order of reactivity for the halogen molecules. Secondly, you have to also remember that the hydrogen is getting substituted by the halogen. So this hydrogen is what type of hydrogen? Primary, right? Because it is attached to primary carbon. So the order of reactivity of the hydrogens, it will be 3 degree greater than 2 degree greater than 1 degree. So these are the two things you'll have to know. First of all, F2 greater than Cl2 greater than Br2 greater than I2. Achha, by the way, F2, the reaction is too violent. So it is not a good idea to try this reaction at all. It is too violent. And iodine is the total opposite. The reaction is very slow and reversible. So like iodine, if you try to do this reaction, it is CH4 plus I2 is CH3I plus HI. So the problem is it is reversible. Now why is it reversible? Because HI is a very good reducing agent. Okay, HI is a very good reducing agent. So to prevent the reaction from reversing, you will have to use a strong oxidizing agent. You can use HiO3, you can use HNO3 also. So you can use HiO3, you can also use HNO3, any one, right? So this and this, they are very strong oxidizing agents. So HiO3 or HNO3, they are such strong oxidizing agents that they will react with HI, and once the HI has been taken care of, then there is nothing to worry. Then this reaction can be accomplished. So these are the two extremes. Fluorine is too violent and iodine is too slow and reversible. So these are some basic details, right? But what we are interested is in the mechanism, because I told you in today's meeting the agenda will be to discuss the important mechanisms in this chapter and discuss the important isomerisms in this chapter. That is the total agenda of this meeting. Okay. Okay, now CS3 Cl is the product. Okay, so let's just discuss these few steps first. Okay, let's just have a quick discussion of these few steps. So, first of all, you remember what I said, that the chlorine molecule has a very high bond dissociation energy. So, if the chlorine molecule has to break, you will need a good source of energy like UV light. So, Cl2 will break into Cl dot plus Cl dot due to the UV light. CH4 will combine with Cl dot to give CH3 dot plus HCl. CH3 dot plus chlorine will be CH3Cl plus Cl dot. Now, at this stage, there are two possibilities. Either the reaction will propagate, means it will continue further, or it will terminate. These are the two possibilities. So, regarding propagation, so CH3Cl plus Cl dot will give you CH2 dot Cl plus HCl, and CH2 dot Cl plus Cl2 will give you CH2Cl2 plus Cl dot. So, this is propagation. Now let's go to termination. Let's have a look at termination. Okay, so this is propagation. Now what about termination? Suppose two Cl dots will combine to give chlorine, then two CH3 dots will combine to give CH3CH3, and one CH3 dot will combine with one Cl dot to give CH3Cl. The point is that termination literally means that the free radicals will exhaust each other. You know, if they don't exhaust each other, then this reaction will never stop. That is the trademark of this reaction, because this reaction is so vigorous that if the free radicals, they don't exhaust each other, this reaction will never stop and you will get propagation continuously like this. It will not stop. So this is the thing, and you can see in this propagation that once you got CH3Cl, it led to CH2Cl2. So further substitution, another hydrogen has got substituted, and then another round of substitution, and then another round. So the substitution will be relentless unless there is termination. So you just need to be aware that termination means that in various ways the free radicals will exhaust each other. If not, there will be further substitution, and I don't think we need to go beyond this. It's quite obvious that after this, the next round of substitution, the CH2Cl2H will go away, right? So, and it will go on, right? So this is the total details of free radical substitution mechanism. So this is the first mechanism in this chapter. So I told you today we will do 4 mechanisms and 2 isomerisms. That is the backbone of this chapter. Once that is done, the rest of the chapter we'll do next week. So now that brings us to the second mechanism of today, which is electrophilic addition, also popularly known as Markovnikov. Okay, now that brings us to the second mechanism of today, that is electrophilic addition, but famously known as Markovnikov. Now in this one, what happens is that there will be one unsymmetrical alkene. So CH3, CH double bond CH2, as you can see it is an unsymmetrical alkene plus HBr. Okay, now uh, speaking of HBr, the reactivity order for halogens is Hi greater than HBr greater than HCl. Okay, just remember this reactivity order, Hi greater than HBr greater than HCl. तो इसमें इम्पॉर्टेंट चीज़ क्या है कि the alkene is unsymmetrical and HBr will generate H plus, and H plus will play the role of electrophile. So electrophile has a natural attraction for alkene because alkene has pi electrons, it is rich in electrons. So electrophile has a natural attraction for alkene. So what happens is that the electrophile will either attack number 2 carbon or number 1 carbon. If the electrophile attacks number 2 carbon, you will get CH3, CH2, CH2 plus, which is a primary carbocation. If the electrophile attacks number 1 carbon, then you will get CH3, CH plus CH3, which is a secondary carbocation. Actually, you may recall from the the previous chapter of organic, that is general organic chemistry, the chapter just before this, you may recall that this tendency is also called electromeric effect. The tendency of H plus to go for the pi electrons, it is also called electromeric effect. So we won't go that deep, we'll just say it superficially. So electromeric effect means that the electrophile will induce a temporary polarity in the bond, like the pi electrons will go to either carbon, and whichever place the pi electrons go, the H plus will also go there, right? So that much detail we don't need to talk about, but you should be aware that this tendency is also called electromeric effect. So the two carbocations which you have got, definitely the 2-degree carbocation is more stable, because we all know that secondary carbocation is more stable than primary carbocation. So definitely this is more stable, and since this is more stable, this is the one which will take the whole thing forward. So CH3, CH plus CH3 will attack by Br minus. So CH3, CH, Br, CH3. So this is the answer that you will get, right? This is the final electrophilic addition product. So in the end, the nucleophilic part of the reagent Br minus has also got attached to the compound, right? But we call it electrophilic addition. Why? Because the initiation is done by the electrophile. Both H plus and bromine have got added to the compound, but it is called electrophilic addition because H plus is triggering the reaction, right? Another thing is this electrophilic addition mechanism is also called Markovnikov rule. So what exactly is the rule? So this scientist Markovnikov, he made a statement that when a halogen, when a unsymmetrical alkene is attacked by a reagent, okay, when a unsymmetrical alkene is attacked by a reagent, the negative part of the reagent goes to the carbon with lesser hydrogens. So the negative part of the reagent is Br minus, it will go to CH. This is the exact statement of Markovnikov's rule. The negative part of the reagent goes to the carbon with lesser hydrogens. So this is the full details of Markovnikov's rule. right? Okay, now the contrary to Markovnikov is anti-Markovnikov, and that was given by a scientist called Kharash. So it is also called Kharash effect. So it is the contrary of Markovnikov. Okay, it is also called anti-Markovnikov. Okay, so let's have a look at the mechanism of free radical addition, that is Kharash. Let's see the mechanism. Uh, so basically CH3 CH double bond CH2 plus HBr. This is the organic peroxide, benzoyl peroxide, C6H5CO whole twice O. So this is benzoyl peroxide. So CH3 CH double bond CH2 plus HBr in presence of benzoyl peroxide is CH3 CH2 CH2Br. Okay, so you can see that this is a complete opposite of Markovnikov. So that's why we say anti-Markovnikov. So what is the mechanism? Now C6H5 C double bond O C double bond O C6H5. It will undergo homolysis, right? Homolysis means it will split into free radical. The opposite of homolysis is heterolysis. So these are all very basics of organic chemistry. So through homolysis we will get a free radical. So 2C6H5COO dot. This further will create a free radical C6H5 dot. Now C6H5 dot plus HBr will undergo homolysis to give C6H6 plus Br dot. Now this Br dot will become the free radical which will add to the alkene. So CH3 CH double bond CH2 plus Br dot. So Br dot will now add to the alkene. So Br dot can add either to this carbon or to this carbon. So if Br dot adds to this carbon, you will get a primary free radical CH2 dot. If Br dot adds to the last carbon, you will get a secondary free radical CH dot. Now all of you are aware that secondary free radical is more stable than primary free radical. Just like in the previous mechanism of Markovnikov, the secondary carbocation was more stable than primary. So the carbocation stability and free radical stability is playing a role. So this is more stable, so this will lead to the final product. So CH3 CH dot CH2Br plus HBr. And now as per the discussion, the Br has already got added. So the CH3 will now accept the hydrogen part of the reagent and you will get CH3 CH2. Yeah, you will get CH3 CH2 CH2Br plus Br dot, right? So this HBr will split into H dot and Br dot. H dot will get attached here and you will get out Br dot. So you can see that this is the mechanism. It is called anti-Markovnikov, but it is free radical. The other one, Markovnikov, was electrophilic addition. This one is free radical addition, right? But it is called anti-Markovnikov because the result is the exact opposite of what you expect in Markovnikov. So if you look at HBr, HCl and HI, if you look at these three, then HBr will give free radical addition, but HCl and HI will not give this reaction. Why? Because in HCl, the bond between H and Cl is quite strong, and because the bond between H and Cl is strong, uh, in this fourth step, this free radical will not be able to break this bond. So the bond between HCl is too strong that in number 4 step, this free radical cannot break the bond. So HCl will not give anti-Markovnikov. HI, the problem is the opposite. In HI, the problem is that the bond is too weak, and there is a possibility that the I dot free radical will combine with itself to give iodine. This I dot free radical will combine with itself to give iodine. So you will not get any mechanism at all, because the I dot radical only will not be available for the mechanism. It will combine with itself and generate iodine. So that is the total details of the mechanism number 3 for today, that is free radical addition. Okay, so next we come to the mechanism electrophilic substitution. So this is benzene. So benzene plus ENU. ENU is the reagent. So why have I written ENU? Because the reagent has a electrophilic part, that is E, and a nucleophilic part, that is Nu. So after the reaction, the electrophile part will get attached and you will get Nu minus. Now ENU, these are the steps. Like ENU will split as E plus and Nu minus. Then E plus will attack benzene. So when E plus attacks the benzene, what will happen is that this pi bond will break. Okay, this pi bond will break and it will be used to make a bond with this electrophile like this. The hydrogen which was over here has been shown and the hydrogen over here has also been shown. But because the pi electrons have gone away, so this particular place has become a plus charge. So it has become a carbocation. Now because it is a carbocation, the negative part of the reagent, the nucleophilic part, Nu minus, it will now come into the picture. So it will attack the hydrogen, and when it attacks the hydrogen, the bond over here, the electrons will come inside. So you will have electrophile attached like this, there will be a bond over here plus NuH. So this is the mechanism of electrophilic substitution. So in electrophilic substitution, what is happening, that the primary thing is the aromatic ring, the benzene ring. It is being attacked by a reagent which has got an electrophilic part and a nucleophilic part. The electrophilic part is initiating the reaction because the benzene ring is rich in electrons. So the electrophile will go towards the ring and it will get attached to the ring like this. But this is not something which can sustain because it is a carbocation. So carbocation will now be attacked by the nucleophile. Nucleophile will take away this hydrogen and you will get the substitution product. So why is it called electrophilic substitution? Because at this particular position there is a hydrogen that has been substituted by the electrophile. So this is the mechanism of electrophilic substitution. Okay, first example is halogenation. Okay, first example is halogenation. So this is the benzene ring plus this is the halogen. So this is the benzene ring plus Cl2 anhydrous AlCl3. It is giving chlorobenzene plus HCl. So this is halogenation. This is the example: benzene plus chlorine Cl2. Catalyst anhydrous AlCl is in chlorobenzene plus HCl. Now what are the mechanism steps? So the first step, what is happening? is that chlorine is attacking AlCl3 to give Cl plus and AlCl4 minus. So this Cl plus is the electrophile. The second step, the electrophile is attacking now. So Cl plus will attack and you will get this carbocation. So this is the carbocation is attacked by AlCl4 minus. So Cl2 plus AlCl3 is Cl plus AlCl4 minus. Like I said, Cl plus is the electrophile, this is the carbocation. Carbocation is attacked by AlCl4 minus to give chlorobenzene plus AlCl3 plus HCl. So yes, the catalyst is taking part, but it is getting regenerated in the last step. That is one of the ways of catalytic activity. The catalyst can regenerate and come back in the last step. Okay, so this was number A, that is halogenation. Now there are a few more important electrophilic substitution reactions, but they are almost the identical method to this. So I'll just tell you just the first step, that is so Friedel-Crafts alkylation. So CH3Cl plus AlCl3 is CH3 plus AlCl4 minus, and finally Friedel-Crafts acylation. Okay, Friedel-Crafts acylation. So CH3COCl plus AlCl3. So this will give you CH3CO plus and AlCl4 minus. So I think you can now understand what will be the final product, because the electrophile I have shown. So this will ultimately give you, when with benzene, toluene, benzene with CH3, toluene, and this will ultimately give you acetophenone, benzene with CH3CO, it will give you acetophenone. So that is number B and number C. Okay, now in nitration there is just one exception, that the electrophile in this halogenation, Friedel-Crafts alkylation and Friedel-Crafts acylation, the electrophile is generated in the first step in one shot. In nitration what happens, this is sulfuric acid and this is nitric acid. Now sulfuric acid and nitric acid, when they react with each other, then you get this one, protonated nitric acid. Protonated nitric acid plus HSO4 minus. This protonated nitric acid gives water molecule plus NO2 plus, and NO2 plus then acts as a electrophile. So the electrophile generation, it happens, that step, it happens in two parts. So first you get protonated nitric acid and then you get NO2 plus. The other thing is that in this reaction, you will notice that HNO3 is accepting a proton from sulfuric acid and sulfuric acid is giving a proton to HNO3. So this is a very rare reaction where the HNO3 and H2SO4, which are both very well known as acids, one of them is acting like a base, HNO3 is acting like a base, it is accepting proton. The other one, H2SO4, is acting like an acid, it is surrendering a proton. So that is a very interesting thing about nitration. So that completes electrophilic substitution. So we have discussed the four mechanisms today. That is so we have discussed free radical substitution, electrophilic addition, free radical addition, and electrophilic substitution. So we have discussed these four mechanisms, right? Now, I had mentioned earlier that after discussing the four mechanisms, we will be doing this isomerism, two types of isomerism that is important in this chapter. One is conformation isomerism that is applicable to alkanes, and the other is geometrical isomerism that is applicable to alkenes. These are the two important isomerisms in this chapter. So now we will discuss those, and after discussing those, this session is going to be concluded after that discussion, and in the next session we will do the remaining part of this chapter. Okay, now we will discuss the two types of isomerisms. First is conformation isomerism. This applies to alkanes. Look at the structure of ethane, C2H6. So ethane, C2H6 is CH3CH3. So this is called eclipsed. So the rear carbon is being eclipsed by the front carbon. This is the front carbon, the rear carbon is eclipsed by the because you know the three hydrogens are oriented in the same way as the front three hydrogens, so it is fully eclipsed. Then comes staggered. In staggered, what happens? The orientation of the rear carbon is totally dissimilar to the front carbon, so you can clearly see all the three hydrogens at the back. So this is called staggered. Now eclipsed is the most unstable, okay, because there is a steric factor, because they are in the same line and there is a steric factor. Staggered is the most stable because they are not in the same line, so there is a steric factor is less, right? Now okay, now there was a scientist called Newman. He gave a suggestion that the front carbon you can show it the way it has been shown over here with the three hydrogens, but the rear carbon, the back carbon, you can show it with a circle, and you can show the three hydrogens coming out of the circle like this. And in eclipsed we say the dihedral angle is 0, I think you understand what it is. The angle by which the back hydrogens are displaced with respect to the front hydrogens. That angle is called dihedral angle. So in eclipse, the dihedral angle is 0 degree, and the torsional strain, which I was telling you, steric factor, torsional strain is maximum. In staggered, this angle is going to be 60 degree. So the dihedral angle is 60 degree, and it will have minimum torsional strain, because over here, as I told you earlier, that the steric factor is the lead. So this has got minimum torsional strain. So that means the eclipse has got the worst stability, and staggered has got the best stability. Another thing, you can have dihedral angle between 0 to 60, like 0 is eclipse and 60 is staggered. You can have dihedral angle between 0 to 60, then that one is called skew. So skew literally means that dihedral angle will be between 0 to 60, right? And therefore the stability will be not as bad as eclipse, but it will be better than staggered. So this is the total details about conformation isomerism. So the thing is that geometrical isomerism, this is called cis and trans. The bulky groups are on the same side of the double bond, that is called cis, and the bulky groups are diagonally opposite side of the double bond, that is called trans. Acha. Now this dipole moment of trans isomer is coming 0 in this case. In this case, dipole moment is 0.33 d. So that means that cis isomer is more reactive, because cis isomer has got a reasonable amount of polarity. Trans doesn't have any polarity, so trans is more stable, cis is more reactive. And you can also see that the boiling point of cis is 277, but trans is 274. Now, in today's class, both these isomerisms which we are discussing, whether it is conformation isomerism or whether it is geometrical isomerism, the underlying concept is whether you can have rotation about double bond and rotation about single bond. That is the underlying concept. So actually what happens is that when we were doing alkanes conformation isomerism, there to rotation is there actually rotation is their rotation is actually hindered by the repulsions between adjacent bonds. So the repulsions between adjacent bonds hinders the rotation. And in case of alkenes, here rotation is impossible because there is a pi bond, and pi bond is lateral overlap, so it acts like a lock, so rotation is impossible. So both conformation isomerism and geometrical isomerism, the underlying principle is that whether rotation is possible about the bond or not, and no, it is not possible, and that is why you have conformation isomers and that is why you have geometrical isomers, right? Okay, if you are talking about solids, then trans isomers have higher melting point because trans isomers, they fit very well in the crystal lattice. So if you are talking about solids, then trans has higher melting point. If you are talking about solids, then cis has lower melting point because cis doesn't fit so perfectly in the crystal lattice. So, and not to forget that cis and trans isomers, they are also called stereoisomers. Okay, stereoisomerism is a special kind of isomerism which is totally dependent on the spatial distribution of the atoms and molecules. So it is a kind of stereoisomerism, cis and trans. And of course there are other stereoisomerisms also, like optical isomerism, right? Okay, so we have completed the targeted topics for today, the 4 types of mechanisms, and we have also completed the 2 types of isomerism. So the targeted topics for today are over. So I'll conclude this session, and in the next session we will do the remaining part of this chapter, that is hydrocarbons. So we'll continue that the next Wednesday, right? Okay, I'll end this session. Bye all of you.